All right, so confidence interval for hypothesis test for proportion. And the data we're going to look at here is, does the home team have an advantage? What's the common belief about home team advantage? What do you think? I'm thinking home team has the advantage, right? Because they got their crowd cheering, woo! They're comfortable in their spot. So we think that there should be more wins when a team is at home than when they're not. And there's some data on this in StatKey. So let's switch this up here. Let's see, we are looking for hypothesis tests for a proportion. And the data is already in here, I think. Soccer, home wins. All right. So there were 120 games that were looked at. 70 of those games, the home team won. So this is our sample data. So let's talk about population and sample and statistic and all that fun stuff. So what's my population here? How about any sports team? That plays competitively? Yeah, home team is supposed to have a higher proportion of wins is what the belief is. So any sports team that plays, let's go competitively, although it's not competitive, who cares, right? And our parameters, so there's lots of things about sports teams that you can record, and winning is a big one. So that's our parameter. Proportion of home game wins. And the question is, does the home team have an advantage? So that would mean we think that they would win more than half of their games. I'm going to just call that a greater than. So I'm going to say my alternative hypothesis here is that P is more than 50%. Right? That would indicate the home team has an advantage. And if they don't have an advantage, then it should be about, half the time they'll win at home. It's just a random chance thing, like flipping a coin. Could win, could lose, equal probabilities. So H, 0, null hypothesis, I'm going to go with P equals 0.5. Right? So it's like flipping a coin. They either win or they lose. 50% chance they'll win, 50% chance that they'll lose. If there is a home team advantage that it matters being at home, then we expect it to be greater than 50%. So that would be our alternative hypothesis there. Next thing we have is we have some sample data. So sample 120 soccer games. And the statistic is that 70 out of 120 is the proportion of home team wins. In statistics notation, the population proportion is a P. The sample proportion is P with a hat over it. So we're saying our sample proportion is 70 out of 120. StatKey said that was about 0.583. I think the threes keep going on that if we had another calculator. So 0.583. So the question is 58.3% significantly higher than 50%? And the answer is sometimes it is, sometimes it isn't. So that's why we have to run a hypothesis test to see, is this really higher enough to say, yeah, it looks like there's a home team advantage here. So that's when we have to do our sampling distribution. So in this case, the data was already here. StatKey already had the null hypothesis set for me, and they already had the sample data, so I don't have to do anything special except start generating, and go for 7,000 today. Okay, and then StatKey says you have 7,000 new samples here. Every sample is 120 in size, and so as I move through here, I can see that the numbers over here are going to change, except the sample size ain't going to change. And I can see all kinds of different things happen. So sometimes, based on this original data, there were only like 50 out of 120, right? So that's less than 50%. Over here, they're right at 50%, 60 out of 120. Over here, there were 69 out of 120. So what is it? Significantly higher means I got to be out here in the tail somewhere. So to see if my data is out there, I then run, in this case, a right tail test, because my alternative hypothesis was a greater than. The alternative hypothesis always tells us which test to run. And then StatKey automatically puts 2.5% in the upper tail. And usual cutoff, this is not super important, so we would just go for the 5% rule. So with the 5% rule, if I put 5% in that tail, then StatKey says, if you find a sample upsize 120 where more than 57.5% of the home games were won, then that's unusually higher than 50%. Mine is 58.3%, which is higher than 57.5. So my data lives out in this red region right here, indicating that I should reject the null and accept the alternative. To get my p-value, I actually have to plug in my sample data down there on the x-axis, 0.583. And StatKey says, okay, you get about a 4% significance level. Ooh, 4% is kind of close to 5%. I'm gonna write that down and then do this again just for fun. But my guess is it's gonna always be less than 5%. 120 is not a big sample, but it's not a small one either. So based on my null hypothesis here and my sample data here, I'm just gonna make a note that I got a p-value at the moment of 4.2%. And if I went with the standard alpha of 5%, right, we're definitely less. So this is saying, ooh, you should reject the null. Reject null. Draw my little sketch next. I'm going to run it again just to see if this is borderline. So what am I sketching here? This is a sampling distribution. For proportion of home team wins. Samples size n equals 120. And in the middle of this, I expect it to be about 50%. That's the P, the null hypothesis. I found that my sample data ended up being out here-ish. So that's my P hat, 0.583. And StatKey said the other samples that are higher, about 4.2% of other samples of size 120 will have a higher proportion than yours. And that's what we call our p-value. It's less than 5%, which is the usual value for the significance level alpha, which again tells us our decision should be to reject the null. So that means the data supports the alternative hypothesis, so we write up a conclusion that says that. So we have significant evidence. So this is my conclusion. Press release. Ooh, sorry, I off. Conclusion. What's the probability that I remember to turn my phone off before class? I think it's about 50%, unfortunately. look back at the videos. Conclusion, we have significant evidence. Oh, I said I was going to double check this, didn't I? Is it really significant? Significant. Pause here, evidence. I think it's still going to come out significant. If I reset and run again, 7,000 again, like before, right tail, and then we enter our sample statistic down here on the x-axis, 0.583, and I get about 4% this time. Yeah, that's even smaller than last time. So my guess is that it's always going to be near 4% if we keep running this over and over again. Yes, so I think we still do have significant evidence, unlike last time where it was kind of squishy there. So we have significant evidence that the home team has a higher chance of winning a game. Has a higher chance, right? That's the advantage. That's what we mean. Higher chance of winning. Conclusion. Interpretation of the p-value. Let's look at that again. What does my p-value mean? So an interpretation wouldn't be to say, hey, the p-value is 4.2%. That's just a statement, right? What does it mean? Wow, 4%, 4.2% of what? So that's the interpretation part. So the interpretation is that's the percent of other samples that will have a proportion higher than ours, assuming that it was supposed to be around 0.5, right? And that assumption is important because that gives us this spread here. So p-value, so there is a 4.2% chance from my first simulation of finding another sample of 120 games where the home team, I just want to put it in context, won more than 58.3% of the time. Oh, I'm running out of room here. When we expected about 50% wins. Okay, so assuming the average was supposed to be about 50%, what's the chance of getting more than what our current sample is? That's a p-value. 4.2% chance of that happening. We say, yeah, that's significant. So what that means is if this is the typical kind of sample, then the home team seems to win more than half the time. Okay. Next, we're going to look at a couple of new ideas related to this and review some old ideas. But first,